studies of quantum mechanics and special relativity. And I said that addition is very, very non-trivial and challenging. And it took 30 years or more, actually, to figure out consistent formulation of that, right? And then we say, okay, we're not going to go through 30 years of work, obviously, but at least we can taste of it, how challenging that was. So we start by saying that if we want to do this is sort of review. The easiest approach to that is, for instance, okay, in the case of non-relativistic quantum mechanics, we particle. So here is our Hamiltonian, and we solve the system by analyzing momentum eigenstate, because momentum is momentum commutes with the Hamiltonian. So we first get a complete set of states. Then we can look at the time evolution if you want by just looking at this diffusion equation, first order equation, which is equivalent to the statement that state evolves according to unitary evolution, right? So quantum mechanics is all about unitarity. So then we say, okay, looks like then I can do it because a relativistic Hamiltonian sounds like I can just write it down. And you can say, what's wrong with taking this as my Hamiltonian, go through the process? Looks like relativistic quantum mechanics. Looks like I'm done with it, right? The goal is to see something is wrong about that. And so we started our discussion about understanding what is special relativity, first of all, partly review, partly setting up a notation, and some of them might be new to you. And we're saying the relevant space-time geometry for special relativity is what's known as Minkowski space-time type, which is 3 plus 1 dimensional flat space of time, 3 for space, 1 for the time. So for each point on that 3 plus 1 dimensional flat space and time, we say, okay, let's introduce a coordinate system that labels time and spatial vectors. Likewise, we can also introduce momenta, which has energy and momentum with it. Now we say, oh, there is a notion of invariance of this space and time. Okay, so that set of invariance leads the Minkowski space-time in type is what's known as fully Hong group, which I will discuss today. But there is a subset of that, which is known as the Lorentz group. And then we go through the definition of the Lorentz group, which was basically given a metric. We say, oh, what are the set of transformations, in particular linear transformations, which is x independent, that leaves the metric invariant. A metric measures local geometry, distance, eventually, or cover transform numbers. So we say the definition of a Lorentz group is a set of transformations lambda in such a way that did I use sigma rho? I forget. Doesn't matter. Rho mu sigma nu is equal to mu. Okay, so the set of such transformations leaves the metric invariant is the Lorentz group. It forms the group. So okay, so that's more or less where we ended. I mean, we talked about the inverse metric, which can be defined as mu alpha nu. So this is the metric G. This is a notation for inverse metric. So because of the meaning of the inverse, it should be equal to delta. So that's therefore notation for inverse metric. We're going to just use raised indices. And we said the metric can be used to lower or raise indices, right? So given a vector a0, we can lower that by contracting with this. This will give a covariant vector starting from contravariant, or you can do the other way around, starting from lower vector, you can raise the index. So you can go back and forth. So this provides a map that maps from contravariant to covariant vice versa. All right. So, and another key point was such a transformation by construction leaves inner product invariance. For instance, this ends lambda A dot lambda B, which okay. So that's model content we talked about last time. Yes.
You have said that the metric tensor is two tensor.
It is a two-index symmetric tensor. Yes.
It doesn't seem like tensor is like a tensor.
Why? This is the
Then a tensor must be different from the original one, isn't it?
so this is how this expression is G prime of mu nu is equal to that is equal to the original one. So this equation has two meanings, as you said. A, G transforms as a tensorial way because this is G prime. B, that transformed guy is the same as original guy. So there's invariance to it. So this is the combination of tensorial transformation combined with the fact that there's invariance property. Good question. Any other questions? All right. So now we're going to talk more about the details of Lorentz group, and we will come back to this question once we build language to tackle the question. Okay, I said that the set of those transformations form. And in particular, the structure of that group is mathematically set of orthogonal matrices, which is total 4 by 4. But there is a difference. There is distinction between space part and time part. So I'm just writing this way. Okay, this notation means that set of orthogonal matrices defined with respect to the matrix, but the matrix has a signature that distinguishes the one from the rest. That's what this is. Okay, good. Now let's analyze this group a little bit further. Okay, I mean, if you never heard of or learned about group theory, don't worry about too much. Just try to stick to my discussion. Yes.
Why don't we consider the special orthogonal group?
Good. So that's the next thing I'm gonna do. Yeah. So the question was why can't we just look at the special orthogonal part of the group, not the full or all? Okay, that's exactly the next thing I'm gonna do. Any other question?
로렌츠 그룹이 5, 3,1에 포함되는 거지 5, 3,1이 무조건 로렌츠 그룹은 아닌 거죠.
Which I will clarify too. So the question was, is full this thing is Lorentz group or actually only the special sub part of that? The answer will depend on who you talk to. If you talk to mathematicians, absolutely this is my Lorentz group. Don't even ask me. If you talk to physicists, most of the physicists, they will say, "Why are you talking about this? It's not Lorentz group." Let me clarify. So the whole of it. Any other question? Good. Let's talk about it. All right. So this is a rather big group. Okay. In order to do that, here is a strategy I'm gonna tackle. So I'm gonna restrict to the subgroup of this thing. Okay, meaning subset of elements which also form a group. I'm gonna look at the part that the determinant of lambda is +1, which I will discuss. So this part in the physics contest say proper. 2, or mathematicians will say spatial. Is that a consistent choice of word? Proper? Anyway, whatever. So then the next thing I'm gonna look at is we're gonna focus on the choices of lambdas where whose 0, 0 component is greater than 1, which I will again discuss. And this part is called orthochronos. So eventually, mathematically, this part justifies the fact that any orthogonal matrix that has a determinant 1 is called a spatial orthogonal group. Okay, spatial means determinant is 1. So subset of that thing is this. So this first of all forms a subgroup. Second, any element, regardless of this property that satisfies this is also forms of. So in this case, whenever it satisfies this property, I'm gonna write it as something with the plus sign. Okay, because it is greater than +1. So if I combine these two, then eventually we are focusing on subgroup that satisfies both of these property, which mathematically S of plus 3,1, the name is proper, also pronounced the rest. Now, when we say I want to study relativistically invariant quantum field theory, we mean that the theory being invariant under this, not full this. So if you ask the physicist, okay, you're talking about Lorentz group, you mean this? They say, no, I mean this. But they mentioned, hold on a second, we have this set, we have to study an entire set. I want to classify things, right? So they have to look at the entire thing. You might say, am I looking a lot of information by constraining myself to this subsector? The answer is, of course, yes, because we're looking at a subset of it. The good news is that you can recover the entirety of this original thing. So you can get the entire part of it by having two extra discrete transformations. So take any such transformations, and then you can go reach entire rest of the element by having two special discrete space-time symmetry. The first one is called parity. And the second one is called time reversal. So parity, the matrix representation is this. So in more mundane expression, what it means is that it flips the spatial vector component to minus of that. Okay, so literally you do the mirror transformation. Time reversal, as the name suggests, in this case, you're just flipping the temporal relation. So the claim is that first you analyze this part, which I will give you slightly better motivation for doing that. Then take any such component and then compose with either P or T or PT. You can reach the rest of the element here. Okay, so that's the structure of a full all three component. Yes.
You mean by similarity transformation?
If you can do that way, yes. I mean, so similarity sometimes means something very specific, but here I just mean that suppose I have some element of G. Well, I never used G before. Did I? Well, why am I even using it? So given a lambda, which is element of plus, well, you'll see some people put the plus side there. I mean, it doesn't matter. You know what I mean? Plus. Then what I'm saying is that you can take this, you can do, so mathematical form looks like similarity transformation, like this, or G, or ET. I'm saying you can get an element now, because this has manifestly negative parity, right? So this also has a negative, sorry, what am I saying? This has manifestly a -1 determinant, right? This has an ability to flip the temporal side of the temporal component. So in order to reach the rest of it, either you have to have a discrete symmetry that turns determinant -1 to determinant +1 transformation, or you want to have another discrete transformation that goes from the positive temporal direction into the negative temporal direction. That's what time reversal is. Okay, so basically you can just map out the rest of it.
Is this the parity representation is similar to the metric you have written down?
It happens to
Does
be
that mean the parity is always conserved, you mean?
parity is no. So good. So that's good questions. You might say, your question can have two aspects to it. Either just mathematically, whether just definition of isometry already ensures that the parity must be preserved. That can be one aspect of your question. I don't know what you were thinking, but I'm just saying what I'm thinking. And the second aspect of your question could be physically, in this universe that we know today, whether parity is preserved or not. Mathematically, I'll say that the parity is part of the isometry, just mathematically, in principle. Okay, because that comes out of the isometry, which was literally all 3,1. So it's part of it. However, physically, turns out that this universe does not respect the parity nor time reversal. So it breaks both of them. So we have a good physics reason to focus on just this proper orthogonal part of it. Because we know that our universe does not respect discrete symmetries. Therefore, it doesn't respect the full all 3,1.
My question was that the parity you have written down, the matrix representation of parity.
Yeah.
Is just the same as the metric tensor you have written down, so.
That's right.
Yeah. So that, and you have said that that matrix always conserved by any Lorentz group transformation, right?
Yeah.
Then that means the parity should also just transform the same.
So okay, I see. Thanks. So the answer is not quite because so that's why here I put with 100% confidence equal sign. And you recall that when I write metric as equal to this thing, I always put the quotation mark. And I explain to you why I did that. Because metric as a 2-index symmetric tensor actually does not get this matrix representation. So this is generally one up, one down indices. Okay, lambda, mu, nu. So it is actually matrix. So they are different tensor. So that translation. Okay, I see the temptation because metric picture, so that's that. But actually, mathematically, it does not depend on that. Thank you. Yes.
If we perform the similarity transform with P, then does it just preserve the difference? So maybe we should.
Good question. Yeah. When I was saying that, I was writing this. I was hoping somebody asked the question. So naively, no, because determinant of that thing is just the determinant of that, which is the one. But without going to all the detail, so let me just claim, okay, because that's yet another direction we have to explore. Claim is that some of those transformations guarantee that you can flip the determinant of it. You can do the exercise, which I'll show some version of exercise now. You can generalize including PT, and then you should be able to see complete the parity. Sorry, complete the determinant. Okay, but this alone will not suggest that. Yeah, I agree with you. Okay, another question. Yes.
Can you be more specific about how our universe is not obeying parity symmetry or time?
Good. So that should be QFT 1, 2, maybe 3, of course. So that you need to learn about the standard model of the particle physics. And the standard model has what's known as electroweak sector. That is 4 force mediators, 3 massive gauge was known as WZ, and 1 massless guy known as the photon. And there's a strong sector. And strong sector has 8 different kinds of gauge was known as gluons. Now, in the weak sector, electroweak sector, there is this particular quantity known as a CKM matrix that basically turns in the weak process one kind of fermion into the other by emitting some gauge bosons. Okay, it's called the flavor changing processes. And turns out that matrix, CKM matrix, has a complex gauge which captures the CP violating effect. Where we here, in addition to the P, I'm also adding another discrete image known as target conjugation. So it turns out the minimum suggests that the size of CP violation, which includes parity, is over 1, meaning it's just broken. So therefore we know by measurement that P is not conserving. And there are other observables too. Great questions. Let's move on. Okay, so I just claim I can do this. So let me quickly demonstrate why I can do this. Okay, so in order to see that, first of all, let's focus on the definition of it. Lambda, mu, rho, no, that's not that one. Lambda, mu, rho, lambda, nu, sigma, g, rho is mu. So if I take the determinant of this thing, well, if you really want to do it, you may want to raise something with G, because this is not quite matrix yet, as I emphasized several times. So you can raise with something like new alpha. Now this is determinant. Now this is the matrix. Everything is matrix. Okay. So now you can take the determinant of it. So that could get that this is no. The determinant of square is 1. Okay. Because that thing is the same. Basically, the product of two matrices. So the product of determinant. So this shows that because we are talking about the real, this is orthogonal group. This is not a unitary group. If you remember from quantum mechanics, orthogonal group is a real matrix. Unitary group or Hermitian matrix can be complex. Okay, so this is real. That means that this should be plus minus. Okay, so therefore, entire sector divided into two sectors. One has a determinant +1, the other has -1. Okay, now. One thing special about the lambda equal to +1 proper part of the Lorentz group is that because identity matrix itself has a determinant equal to 1, which means that all of the elements living in this sector can be continuously connected to the identity operator. Okay, let me say that again. Every operator living in this sector, which has the determinant same as identity operator, therefore it can be continuously connected to the identity operator. Meaning, now I can talk about the notion of infinitesimal transformations because I can just continuously connect to it. I can just walk away from the identity infinitesimally small amount. The other sector, you literally need a discrete flip, right? So that sector's operator or element cannot be connected to the identity with this smooth, continuous connection. Okay? So that's why this is a special sector, because we have a notion of small rotation. We have a notion of small boost, right? So the phenomena that we have observed has something to do with the fact that we can talk about small transformations. Okay, so that's the first part of it. Second, so from this definition, let's look at the 0,0 component of it. So I'm just kind of take mu equal to 0, and then nu equal to 0. So I'm just gonna look at the 0,0. All right, so I have to take a 1, 0, 0 there. So let me first write. Now, the space and time I'm looking at, it has a structure where this is diagonal matrix, right? I mean, diagonal structures. Okay, but now, all right, too much. From now on, I'm just gonna abuse to say the matrix for G thing. You know what I'm talking about. Do we have a deal? Okay, good. So I'm just gonna take, so this is a diagonal. I'm be careful already. This is diagonal, which means that it can be decomposed as 0,0 part of it, which is 0,0,0,0, which is 1 square. And then I can look at the I component, which is -1. So I sum over, I have I0 square. When I say that, I'm summing over I, right? So, okay, well, I mean careful now, but eventually I will start becoming a slow. All right, so this is one. Okay, so that we know. That means that square of the 0,0 component is equal to 1 plus I0 square, which is manifestly positive or equal to 0, which means that this square should be equal greater than 1. Again, we are looking at the real matrices. So this thing can be divided into two sectors. One is that, the other is this. So far, so good? Yeah.
Can you explain why the Lorentz group is always real?
Okay, good. So the structure is this. If you buy that for the moment, you may say, I'm not gonna buy it, but then we need another conversation. So for now, well, you have to buy it, which I can also explain. So if you buy this orthogonal matrix, so let me just summarize the fact. If that's enough, good. If not, let's tell. So the real version has symmetric matrix. Let me write symmetric matrix. The definition is okay. Whose complex version we say Hermitian matrix. The real version has orthogonal matrix that satisfies this thing, and then complex version of that is known as unitary matrix. Okay. Now I'm not explaining. I'm not giving you an answer. I'm just trying to remind you that there has been this distinction that there's real versus or complex. Now, physically or even mathematically, one quick way of seeing why this should be real is I am like time equal to 0 seconds position here. Let me make rotation. Oh, here is complex time. Goodbye, right? So, real.
I think I should find out.
Yeah, good. Otherwise, not much. Yeah. All right, so good. So we have 4 different sectors. Now, so this is that component, but there's another fact about this guy, which also should be continuously connected to identity. Why is that? So that let's talk about. Okay, no, I had to finish here. So we good with this, yeah? We are happy. Good. So let's consider infinitesimal transformation. So I'm gonna take a matrix lambda, which I'm not making any assumption about which sector I'm in. Okay, I'm just gonna take any lambda from O of 3,1, and let's just consider infinitesimal transformation, which I'm just gonna write as 1 plus omega. So omega is very small. I said omega is very small, right? Did I say that? I did. That answers why you should be connected to identity immediately. But probably most of you don't see why it is connected immediately. So let me just say, omega is much smaller than 1. Yeah? Good? Which means that this is bigger than 1, but I'm just repeating the equation. Right? Which means that if this has a 1, 1, 1, 1, this little perturbation cannot mask the sign of this part. Okay? Now, I think I realized the one loophole in my argument. My claim was that this must be equal to 1. And then I was gonna say that this is sufficient to say that this automatically belongs to this sector, but actually no, sorry. So I'm taking back this argument, but nevertheless, it's true that if you combine with this fact, and then superimpose with that fact, then you can always write it as 1 plus something, meaning there's notion of infinitesimal transformation, and then it also satisfies the fact that it should satisfy this condition. Okay, so this is the sector we're going to focus for the rest of most of the time, of course. Sometimes you may talk about discrete integrals, but a lot of times we focus on this continuous part. Questions? Yes.
그러면 저기서 점대칭이 이제 다른 섹터로 움직일 수 있는 것 중에 하나가 되는데 점대칭 말고 그 면대칭을 해도 똑같이 디터미넌트가 바뀌지 않나요?
The question was, this looks like taking a point to take a point, and then you pass through the origin and then go to the negative side of that. The question was, can I instead look at reflection of the point with respect to the point rather than the origin? Was that your question? Okay. So there is a notion of that. Such a thing is what is that called? I forget. What's that called? In mathematics sense, it is the orientation reversal operation. Actually, such an operation is very important in the definition of fermion. So not even this guy, or either that group or this thing doesn't include any fermion. So this theory cannot explain or describe electron, for instance. So we need to have a way of enlarging it. And that's where this question about the reversal works. Now, I'm just trying to think now whether some combination of this thing can give you a notion of flipping only one side if I superimpose that with the rotation or boost. That sounds like a good exercise to think about. Okay, so I don't have an answer off the top of my head, but I'm suggesting that if such a notion exists here at all, which I feel like it, then you should be able to find a rotation superimposed with this guy in such a way that only one thing is fully together each time. So I suggest to look into. Another question. All right, so let's now analyze this vector a little bit more. just for fun, should I do it? Let me just mention, but I don't think I will explain at least for a while. So in order to have a fermion, there is what's known as a double cover of this group. Don't worry about it. And this thing called the spin, 3,1. This thing can have heavily ferminated. So our universe, in fact, is most likely, which we don't know, is this thing. Okay, the thing that is fermion, but in this sector. But there are other mathematical options known as the P plus minus P and C. If you have heard of that, but if not, don't worry about it. Let's move on with this much of information. So let's look at the proper orthochronous Lorentz group part a little bit. So let's consider infinitesimal rotations. Let's consider infinitesimal transformations. So I'm just gonna write it as lambda being 1 plus omega. And hopefully you know what I mean, because this is still warming apart. Let me write. That's what I mean, okay? And the entries of this guy, which has 16 entries, must be much, much smaller than 1, right? Good. Now, first of all, from the definition again, which I erased, great. How many times should I write the equation? Try to type. Mu rho, mu sigma g. This thing is boom. Okay. No? Okay. So let's plug in this infinitesimal alpha into this one. So that will look like U rho delta nu sigma. Am I doing right? Am I doing sigma g? So we plug in, and by expand this to over omega, because I'm working at the limit where omega is very small. You should find that one important property of omega is antisymmetric to independence. Okay. So you might say, oh, hold on a second. I've been writing one down, one up. Why all of a sudden you're writing this way? Obviously, there's mapping, right? So eventually, if you just work this out, you'll bring it down the index. So you get this equation. Okay, exercise. Just literally do it and see if you can do the index contraction properly. And just expand up to order omega. Drop omega squared, that's what I'm saying. Okay? So therefore, Lorentz transformation, the parameter of the Lorentz transformation must satisfy this condition. So this is what? 4x4 matrix, which is antisymmetric. I already said that I'm not going to sloppy about matrix versus tangent. Okay. Now, how many parameters do I have? What is the number of independent parameters? What? 1,000? 3? This is 4x4. 6, 7, 8. So, right. So this is antisymmetric, which means the diagonal first must be what? 0. And everything here should be controlled by that thing. Yes? Good. So there's 1, 2, 3 different kind of matrices. Yes? You'll be summing about what? How many? 6. Which means that there are 6 independent sorts of Lorentz transformations which are divided into, which we will get to eventually, 3 spatial rotations. Because we're living in the 3 space-time dimension, right? So there's a rotation with respect to x, y, z. There are 3 rotations and 3 boosts. Lorentz boosts. Schematically, actually not schematically, actually that's correctly. So you should think of a rotation as being mixing spatial ij together, and the boosts are mixing or rotating on themselves, one temporal component and one spatial component. So rotations are mixing among the spatial guys. Boosts are mixing among the time and then have spatial direction. Okay, so there are 3 and 3. Let's move on. 4. Right. Okay. So far I've been talking about matrices. And remember, this thing acts on space-time coordinate directly. Yeah, that's what I've been talking about. None of that is the quantum mechanics yet, right? I'm just literally looking at classical space-time geometry and just thinking about how things are transforming. Okay, so in order to pass on to quantum mechanics, so to do quantum mechanics, what should I do? So for a given lambda, I have to have an operator acting on Hilbert space. So that operator, I'm just going to write it as U of lambda. Okay, so now if I can construct such an operator, then I can talk about quantum mechanical notion of a Lorentz transformation, because I can take this guy, act on quantum states, act on the quantum operators in the Hilbert space. Now, what are the conditions that this guy needs to satisfy? Right? So let's look at the conditions that such an operator wants to satisfy. First of all, they need to be unitary. And quantum mechanics, unitarity. But precisely why this guy needs to be unitary? Let's ask that question. So consider a state, like two states if you like, that lives in the Hilbert space. Right? So I have 2 states. You can think of one electron state, and then say you have a position eigenstate. And you use the construct wave function, right? Contracting them together. So I can look at something like part of these 2. Now, under the Lorentz transformation, each of them are transformed by this, because this is now operator acting on the Hilbert space, therefore state 2. So each of them will transform what? Like this. So this inner product, which captures the entire data about the physics, right? Probability, overlap, and so on and so forth. So this will transform as chi U dagger this. Now, remember, we are talking about symmetry, right? Poincare invariance. Symmetry means that it should not modify or change physics. And the most important class of physics in quantum mechanics is this overlap in a product. So in order to satisfy this, for arbitrary choice of states, right? This needs to be true mathematically for arbitrary choice of states. That means that there should be operator equations that every such realization of symmetry must be unitary. Good? Right. So that probably should have anticipated. Let's move on. Two. So now let's consider infinitesimal version. This is C number parameter. So by C number, I mean, so in quantum mechanics class or quantum field theory, we're gonna have to think separately carefully which one is operator, which one is C number parameter. By C number, I mean commuting number parameter, as opposed to Grassmannian number, for instance. You will see some last in a month or 2, if we go well. All right. So C number means commuting number, just number. So this is the C number parameter. That's the language we're gonna use, C number parameter. And we analyze the property of it, which is antisymmetric and has a 6 independent component. So then u of lambda, which I'm just gonna write as u of plus omega. So I'm just gonna extend this operator, but to leading order in omega, because omega is small by definition here. Okay? So I'm just gonna expand this operator, but leading order in parameter omega. So I should write as identity operator. So let me stress that operator. And then now I'm expanding to leading order in this parameter, but this is the operator that does not carry any Lorentz indices. So I must have some guy, I don't know, that at least make it Lorentz scalar object. And you can keep going, really cool. Now, so here again, this is the number parameter. This is an operator acting on a hyperface. Good. Now you might say, "Oh, I see this I. I'm scared. I'm gonna leave." You don't have to, because I will explain that. You say, "Oh, the spectrum of 2. I'm scared. I'm gonna leave now." Yeah, goodbye. No. So if you understand better of the symmetry, this is there are 2 exactly the same guy here, so you just modify by 2 to just not to overcount. Okay. If that makes sense, great. If not, let me explain quickly. So let me just look at I. Suppose that these are antisymmetric, which means that I can write it as ij. I'm gonna just do it once in this class. So just focus. And then these are dummy variables summed up. Yes, Einstein summation convention. 1 up, 1 down. So I'm free to write whatever crazy way you want, but especially I'm just gonna write this way. This is exactly the same thing as that, and then divided by 2. But that thing, if I flip this guy minus sign, and then we will see soon that if I flip this guy, it's also minus the same thing. Okay, so there are 2 of those guys which look the same. Okay, so this summation includes the identical looking guy. So I'm just taking into account that fact. Anyway, so I already used the property of this guy that I'm supposed to show. So let me do it. So is that clear what I'm writing here? Okay, good. So now if you demand that the U is unitary, you should be able to show that this guy should be Hermitian. And then if you use the fact that omega was antisymmetric T number parameter, which I showed using the definition of Lorentz group, then in order for not to be 0, it should be also antisymmetric. Now let's understand what this equation is. Okay, every single time you have an equation, make a friend with it. Okay, so what does this equation mean? So U transformation, meaning there's a Lorentz transformation which realized in quantum space, Hilbert space, right? That thing is first of all starting from identity, which means that you haven't done anything. And you are about to make a symmetry transformation acting on quantum Hilbert space, right? Either operator or state. So by this amount and this guy, the operator appearing in the linear in the parameter for group reason is called the generator. Hopefully I just demonstrated, right? Starting from the identity which you don't do anything, I just about to create omega amount of transformation if I have an operator that looks like J meter. Okay? So it creates this transformation called the generator. There's a more mathematical reason why it's called generator, but the same thing. Now, generator of the unitary matrix Hermitian. If I didn't put I there, which mathematicians will definitely insist on doing that, 100%. Okay? Physicists say, what do you mean? We always put I because we want to be confused about. So if I didn't put there, then you get minus sign. So you're dealing with anti-Hermitian generators. Pick whatever you want. I've just picked it, okay? Second, by the way, this equation should be read as follows. There are, according to this equation, first let's go for you. There are how many generators I'm talking about? 6. So there are 6 generators. Every single such 6 generators must be Hermitian, okay? So this equation contains 6 information. Clear? Okay, good. Let's move on. All right, so let's learn a little bit more about the Lorentz symmetry, realized as a unitary operator in the Derbes space. So the third property that it must satisfy is that it must fulfill group multiplication. So group representation, if you're familiar with, not don't worry about it, means that if you have the lambda 1, lambda 2 of the group, in this case Lorentz group, then suppose I have image of this guy, meaning something that trying to incorporate that transformation in some other space. In this case, we have the U of lambda 1, U of lambda 2, and it says that the representation, among other things. So here I'm not teaching math course here, I'm teaching business course here, but one requirement of representation is that if lambda 1 times lambda 2 is equal to lambda 3, well, I have introduced lambda 3. Then a realization of such transformation or representation also satisfies this relationship, which means that U of lambda 2, U of lambda 1 was equal to lambda 3. U. Some of you understand what I said usually. In quant, okay, should I go on with that? Anyway, you should satisfy this. Okay. Modulo in quantum mechanics, quantum math, possible phase. Meaning, okay, so for those of you who are not familiar with the subject at all, absolutely ignore what I'm saying now. So this equation in principle can have some sort of a phase that depends on this magnetics. Okay, and keep going. And no, okay, and so this thing is related. If you're curious to learn more about it, related to what's known as a projective relationship. But again, at this point, don't worry about it. Okay, so for now, we just take this equation as it is. Yes.
So then if there's something like a Harlow bone effect.
It's related. So it's only very recent realization that this projective representation appearing in quantum mechanics. I'm just saying, okay, I'm just saying it, but don't assume. Okay, I'm just saying, and I'm not gonna go into that. Yes, projective representation is related to quantum mechanical anomaly effect of the symmetry that sometimes has a connection to our parallel bone phase. Okay, I just said 3 keywords, but I'm not explaining. Again, that's contemporary research, even. Okay, anyway, so third property, in addition to that, must satisfy this. Let's explore the consequence of this on the property of a generator that it has to satisfy.
Before you leave that part, could you give me some comment about anti-unitary operator?
Very good. So, yeah, very good. So we talked about time reversal symmetry, and Wigner, who laid out this formulation for the first time back in 1923 or 1926 or 29, one of those 3, 6, 9, one of those years. It said that mean, or prove that, that's what I mean, he's sort of a mathematician, I mean, not sort of, he's a mathematician. Possible realization of a quantum operator of the Poincare group can take either linear and unitary. Unitary understood, right? I keep going whatever. So linear means that linear is that if you have a vector in the vector space like v plus u, and then you have some function alpha beta, and then you have operation e. Okay, so this is the operator. This is some vector living in the Hilbert space. This is the coefficient. Linear means that when it happens, it does this. So it's actually linearly, right? In particular, it doesn't touch the coefficient. Antilinear means that instead, it picks out a complex space. Oh, sorry, complex conjugation. Anyway, now this is linear, this is antilinear. What Wigner said was there are two ways of realizing operators in the Hilbert space, starting from the Poincare group. It should be either linear and unitary or antilinear and anti-unitary. Anti-unitarity means, hold on. Yeah, anti-unitary means what? Do you remember the definition? Who remembers the definition of anti-unitary?
Oh, so sorry, remember u is equal to u equals minus.
That's what I was trying to write, but that is that true? Because that's maybe that's true because that's one of the discrete symmetry that goes the other direction because it is related to time reversal. Maybe that's true. So anyway, so it should be either linear, unitary, the thing that I'm talking about now, or antilinear, anti-unitary. And in the Lorentz group, it is only time reversal operator that is realized this way. The second way. Good. So again, going back to the original plan, this is great, by the way. Okay, keep ask questions and participate. What was I going to say? Yeah, I was going to say, let's study what this group multiplication rule implies on the property of J. Okay, so that gives us what is known as group algebra. Oh, by the way, just one word before we continue. There are many different ways of studying quantum field theory, as you will experience if you pursue. There's a typical way. You do the easy start and continuously confuse. Okay, you start off something, you thought you learn something. Like what about this? What about that? What about that? Never learn about that. Or you take the top start, meaning try to hit the conceptual stuff, whatever. Let's just face it, and half of people may just leave the field, and there might be some people who still survive. Okay, then they just dip more and dip more, getting more confidence and more confidence. Now, what am I doing here? I don't know what I'm doing here, but I'm just gonna take at least something in the middle. Okay, I don't want to take too easy going start, and then like, all right, I have done good luck with the rest of your quantum field theory. So I'm just gonna take a little bit of responsibility here. Okay, that's what I'm going through some of this stuff. I could have written down, this is not a scalar field. Let's just write down Lagrange and analyze. I could have done that. That could have eased my life way more. Okay, but I'm just trying to build it all in case you're wondering what this guy is trying to do. That's what I'm trying to do. All right. Okay, so let's do it. So one version of that thing is follows. Let's take lambda prime and then act with Lorentz transformation, which will look like the inverse here, there, or the other way around, either way. Okay, so this operator acting on another operator as a, if you like, you know, this conjugation operation. Okay, so this thing I'm just gonna write is 1 plus omega prime. Okay, so let's do this different. The first, so this should be equal to by group multiplication law equal to u of lambda inverse lambda prime lambda. Are you with me? So I just literally apply this requirement with the three elements. Okay, good. And I'm just using the fact that the U inverse is the same as U over lambda inverse. Okay, because inverse element should be mapped onto the inverse operator in the Hilbert space. Okay, so let me just try that. All right, so let's expand both sides to leading order in omega prime. Okay, so first of all, left hand side is this, and then I know how to write this down. 1 plus I over this omega prime mu to mu. That's left hand side. Okay, that's the right hand side. In order to do that, let's first understand that. So let's expand, but then one sandwich with the lambda inverse lambda is just one. And then I have lambda inverse omega lambda. Right. Yes. So since I have the form in this way, I can also expand the right hand side, which is one. Now by one, I mean the identity operator. I over 2 lambda inverse omega prime lambda J this. Okay, so group multiplication applied to the infinitesimal version of the acting on the guy that acted by the other transformations. Good, are you with me? Have you left? So let's look at it. The first term is literally 1. If that 1 matches to that 1, so let's drop it. So let's read off the term that is proportional to the leading order or linear order in the omega. So let me write this prime mu nu. I'm dropping I over 2. This is equal to this. So let's work that out. So this, if you work it out, let me just claim for the sake of it, but you can work it out. I mean, you know, you can. But try out one line by including the fact there's an inverse operation. Okay, you should try out. So therefore, this equation should be true for arbitrary choice of parameter, right? So this is true for arbitrary choice of this parameter omega prime, which means once again we get an operator equation. So that operator equation says, no, there's something wrong about this expression on this board. Tell me.
U lambda is not at the left side.
Yes. Who dropped it? You did? I dropped it. So let me put it back. You got what I'm saying? So sandwich this omega j, but where did this guy go? So I have to put back. U inverse j u lambda equal to, okay? So cured. So now, so then again, this equation should be true for arbitrary omega prime. So I should get the following operator equation. So we learned one thing about the generator J U. What is it? It says, let's read the equation. It says this is an operator in the Derbes space, yes? So if I take this tensor valued operator in the Hilbert space, under the Lorentz transformation, it transforms like a tensor. And it is a tensor, not only any random tensor, it is a 2-index antisymmetric tensor. So J nu as an operator in the Hilbert space behave as 2-index antisymmetric tensor operator living in the Hilbert space. Okay, under the Lorentz transformation. Good. So that's fact number 1. Well, like 4. I don't know. Let's continue. Now you can do one more thing. So in addition to this, the next thing you can do is let's also make this infinitesimal too. Yes, there was a question. Okay, you're done. I just good. So let's also make this guy infinitesimal. So what do you see? Take the exact equation. I just first make this guy infinitesimal just to see how generator transform on the finite transformation. That's what I did. Now I'm just gonna make this guy too infinitesimal, and then will give me information about how generator of that guy acting on that guy spits out what happened, right? That's what I'm gonna be. That's what that equation will give me. So it will give me the relation among the generators. Okay, as you'd expect, work it out, you should get the following answer. If you do that, you should get the following answer. I'm running out of space. Oh. Yeah. Okay. So if you do that, you will get this. So this is for Lorentz algebra. So I will tell you. Let me tell you how you might figure out this. I mean, not figure out. The figure out is this thing you have to do. How to remember. So starting from here, this kind of help once my trick. Starting from here, you cut this. You pick the first, and then you write metric the rest this guy. But this is antisymmetric. If I flip this guy, you get the minus sign. And then in that antisymmetric way, I write the same thing. Go back again. If I flip this guy against antisymmetric, so you can pick the minus sign, write it again. If you flip both of them, I pick the plus sign, write it again. So the symmetry property, once the first time is fixed, what I'm saying, should be fixed the rest of it. Okay? So if you get it, good. If not, ask your friend. Or me. But not today, of course. Okay. I have English today. Very important talk after the class. But from next week, I'm yours. Okay, you can just grab me and ask questions. Any question before I proceed? Yes.
Right, the question. What is the the infinitesimal form of lambda minus?
Okay, good. Good question. So the question was, okay, I know how to write this guy, but how about that guy? Is your question, yes? So the thing is, this is 1 plus I over 2 omega dot j, right? And in the unitary operator, inverse is the same as the Hermitian conjugate. You know how to do the Hermitian conjugate of that object, which is 1 minus I over 2 omega, which is a real parameter, j dagger. But we have determined what j dagger needs to be in terms of j. That's Hermitian. So you get it. Another question. Yes.
근데 G가 어떻게 나올 수가 있죠? 람다만 있는 식인데.
G.
그러니까 저 식을 전개하면 람다가 많이 나오고 람다랑 J가 있을 텐데 어떻게 G가 나왔는지 잘 모르겠어서.
Good. So if you plug in both, obviously you will get, lambdas, this and that. But obviously you have to do the gymnastics of the indices to everybody put out. Who does that job? Who can move around the indices up and down? Metric. So if you work it out, you will get it. Yes.
좋은 질문인 것 같긴 한데 저 커뮤니케이터식이 U 시그마가 인덱스가 있는 거잖아요.
Sorry, you're looking here or here?
로렌츠 알제브라 식이
Yes.
근데 커뮤니케이터 안에 지금 오퍼레이터가 들어가 있는
Yeah, so this is a commutator of a quantum operator, and this is genuine commutation relation.
뮤가 저렇게 고정돼 있는 그냥 숫자 아닌가요?
No, like I said,
하는데
J mu nu, there are six, depending on the choice of mu nu, there are six independent choices. Each of them are operator. I told you, you may remember I said that, right? This equation means that there are six different operators. So this tells you like 36 different kinds of operator correlation function, right? In single package support.
그러니까 그냥 가분 통량 그거를 쓰시는 건데.
That's right.
Okay.
So if you like, you can do your math laboratory. Try to work it out component by component, the 636 of one of them, and map, see if they're consistent with this. But here I'm just writing down a single operator equation that takes care of entire 36 equations, a single equation. Yes.
마지막 식을 전제할 때 유니터리 레프레젠테이션이라는 조건을 결국 구하긴 했는데
예.
그냥 레프레젠테이션이기만 하면 저거든요. 유니터리가 아니어도
Well, so if it's not unitary, first of all, then you have to go through the steps where, like a question. First of all, what is this? Right? So you have to have a generator that generates inverse transformation. What is the relation of that thing to the original generator? You have to specify those things. In this current example, unitary was sufficient condition to just give you that condition. Therefore, you can write down everything in terms of a single generator. I mean, by single, I mean a single mathematical expression that generates original dual number. Probably I'm missing your point. If that, please tell me again. I'll answer again.
그렇지만 유니터리한 조건을 사용해서 J가 뭐 퍼미션이라는 조건들을 이용하고 이렇게 전개를 하긴 했는데
Yes.
제 말은 그냥 어쨌든 로렌츠 알제브라지 로렌츠 유니터리 레프레젠테이션 알제브라는
Good. There is a Lorentz algebra which acts on the space-time. There's a Lorentz group that acts on the space and time. What we are doing is we realize that as an operator acting on the Hilbert space. And that I said that because this should be quantum mechanical, every single of those realization should be unitary. Or anti-unitary, anti-linear, blah, blah, blah stuff that I said. Therefore, whatever I'm doing, I want to be maximally consistent with quantum mechanics. So I pinpoint myself to deal with only unitary realization. Did that answer your question? I heard some sounds. That means there's a question or
Yeah, well, couldn't you understand that we are just doing the Taylor expansion of the inverse minus one in that way?
right. But his question was like, why am I using? What can we do without using unitary or hermeticity? I'm saying I'm imposing that as a from the get go. I'm imposing that I only want to look at the unitary operator with the Hermitian generator by putting I there. Because I want to do the quantum mechanics. That's fine. Okay, any other question? Okay, I'm not done yet. I think I have only half of the things that are here. So let's do like 5 more minutes. Very good. But if you have questions, still we can ask. So at this point, let me just quickly say about now Poincare group. So far I've been dealing with only Lorentz group. Okay, so I'm gonna say stuff, and probably I will make over problems such that you can walk through the Poincare algebra thing, basically following more or less the same thing, more terms, more indices. Okay, so logically exactly the same. So let's talk about the Poincare group part. Oh, before that, I have another one thing to say. Okay, good. So within the Lorentz group, okay, so there are J mu nu operators, okay, and this can be subdivided into again how many of this guy? Eventually, six. So I said that I can divide it into a rotation and a boost. So for instance, I can define usual rotation generator, JIJK. You have seen it, right? J123, quantum mechanics, SU2. Creation annihilation, right? You have seen that. And this can be defined as IJK, J, JK. Okay, so there are three of them. These are generators to create SU2 rotation. Oh, actually, sorry. SU2 almost right, but these are generators. Yes, these are generators that actually can create the SU2 rotation. But to be technically correct, so these generate the SU3 rotations. They have ability, they have the potential to generate SU2. And then there's a Ki, which can be defined as I, 0, temporal component. And in terms of this, you can rewrite this. Another good exercise to do is JI, JK, no, JJ, satisfies IJK. Okay. And you recognize this as a literally SU2 algebra. So therefore they generate the rotation. And then JIKJ up to minus plus minus. Should I take the responsibility for minus sign or here in this class or no? Or factor of so too? No, thanks. So then it will look like this, the second one. Now this one you have seen it before, right? In quantum mechanics. This one you probably have not seen it. So let's understand the meaning of this equation again. What does that equation mean? Or in general, how do you read this this type of equation physically? Basically, this means that you pick this K of J phi. Commutator means that you do the rotation by the transformation generated by the first guy, or you can play the other order too. Why is that? Oh wow, I just read that. So if you write down this conjugation operation and if you extend it out, that's why you got the commutator, right? So if you go trace backward, there was a K guy sitting in the middle. You act with the U with the J, and this guy being a generator. So you're basically literally seeing, oh, how boost. Oh, I didn't write down the name. This is the rotation. This is the boost. Three of them. So this boost generator, which are three of them, under the rotational transformation, transformed exactly as a SU2 vector or SO3 vector. That's what this equation means. Okay? So literally there are three-dimensional space. There's a vector, which is a boost generator. And if you do the rotation, it will literally behave like a vector. That's what this equation means. Okay, so Ki is a vector. Okay, so I said I wanted to say something about the algorithm. So Minkowski space and time, the isometry is just more than this 6 kind of transformations. So in fact, starting from the x mu, you can actually do x prime mu is equal to lambda mu x nu. So that's the guy that we've been analyzing. But you can actually do shift. And this captures obviously space and time translation. Check. Okay, this actually solves the definition of being isometry. Okay, so check means trivial check. This is indeed an isometry. You need to know what that means by isometry, which I defined. Okay, I wrote them many times that defining. Check it. So we have to deal with this part. So we have a translation along the three spatial direction. We have translation along the temporal direction. So in addition to now SO 3,1 plus, or if you like, entire 3,1, we have space-time rotations whose group space look like 3,1 four-dimensional Euclidean space. Like R3 means that you can go that direction infinitely, that direction infinitely, that direction infinitely, right? So R3,1 means that I have a three direction, which is spatial direction, which it looks like real direction, and there's a temporal direction, which is also infinitely big. I'm just the distinction. So then there are these two things, but they are not separate factorized transformations. They mix up. One more bit. So mathematically, Poincare group is written as almost, so if I write it as, we're not going to just write it all. So if I write it as this is written as a product group, which means that there are these guys doing something, there are these guys doing something, nothing to do with each other. Okay, but they mix up, and they mix up like this. Don't worry about it, I was saying. Well, this is called the semi-direct product. I mean, we are not gonna make use of much of it, but I'm just gonna define what I mean by semi-direct product next time, concretely, in terms of how things are transforming, okay? So this is the full Poincare symmetry, but if you want to focus on only the proper orthogonal plot, you just look at all plot parts, okay? And I'll finish up the statement about this next time. Then after that, we will start marching on to the naive trial of making quantum mechanics relativistic, okay? And then we will face the problem. Good. That's it for today.